I'm not sure what I was thinking when I drew this graph, or the graph that was here. I've replaced it with a more correct graph, and let's explain how this graph of the capacitor charge or capacitor voltage. Remember, well, not sure how firmly we've established this, but the voltage of the capacitor and the charge on the capacitor are just related by a constant, which is the capacitance, so that the shape of the graph is going to be the same for either the voltage or the charge. So we could label the vertical axis of this graph as either voltage of the capacitor or charge of the capacitor. And I'm going to kind of talk about the voltage of the capacitor at the same time as I'm talking about the charge of the capacitor. I'm going to kind of interchange the meanings of this graph, but hopefully that won't be too confusing. Assuming that the switch is closed, there's a switch somewhere in the circuit. I didn't draw it, but there's a switch here, and we close the switch, or we simply start up the source. There's no charge on the capacitor, so there's nothing to oppose the voltage of the source. So the source will drive current through the resistor as if the capacitor wasn't there, at least for a short time. And it'll take a little while for the capacitor to build enough charge to significantly resist or oppose the voltage of the source. So the voltage in the capacitor starts increasing. The charge on the capacitor starts increasing. As the voltage of the source goes up, the current goes up, which deposits charge on the capacitor at an increasing rate. The charge in the capacitor therefore increases at an increasing rate, and this graph will be concave up for a while. Now that's going to continue until the capacitor builds enough charge to start really opposing the voltage of the source, at which point the voltage of the capacitor gets close enough to the voltage of the source that the current stops increasing, and the charge is deposited then on the capacitor at a decreasing rate, which causes the graph to become concave down. At some point, the voltage on the capacitor will be equal and opposite to the voltage of the source. Now that won't happen until after the voltage of the source has peaked, because the voltage of the capacitor is not going to exceed the voltage of the source. So the voltage on the source peaks here. The voltage on the capacitor, the charge on the capacitor are still building up to some point where the voltage of the capacitor meets the decreasing voltage of the source, and at that point the source voltage continues to decrease while the capacitor voltage doesn't decrease all that much, and the charge starts flowing the other way. The voltage of the capacitor starts pushing charge through the circuit in this direction. And that charge, of course, is going to come off of the capacitor, so that the charge of the capacitor, and hence its voltage, begins to decrease. At some point after the voltage of the source peaks, then at that point the voltage of the capacitor will start to decrease. Now on this graph I've labeled this regime here from here to here, where the voltage of the source is greater than that of the capacitor. Here the voltage of the capacitor and the voltage of the source become equal. The charge on the capacitor and hence its voltage peak, and then the voltage of the capacitor starts to decrease. Now at some point after the voltage of the source reaches zero, the voltage of the capacitor is going to reach zero. And after that point, the voltage in the capacitor and the charge in the capacitor will become negative, faster and faster, then slower and slower, until you have a negative peak or a valley. And this is going to continue, and after a number of cycles, a regular sine wave is going to develop. So what we're seeing here is, shortly after the switch is thrown, we have a transient behavior of the voltage source, of the voltage on the capacitor. and the voltage and the charge in the capacitor will go up, then they'll come down to the negatives, and then they'll come back up. And this is going to continue with the voltage on the capacitor lagging the voltage of the source. Rather, I should say, peaking after the voltage of the source and hitting its valleys after the source voltage hits its valleys, hitting its zeros after the source voltage hits its zeros. And again, after several cycles, a regular sine wave develops. This is not yet a regular sine wave, but we can see how we could approach it. When you solve a differential equation for this sort of a system, you will get a transient and then a long-term behavior. Long-term behavior is the regular sine wave. The transient behavior is the circuit falling into its natural oscillation in response to the driving voltage of the source. In this last figure, we depict voltage of the source, voltage of the capacitor. Remember again, the voltage of the capacitor peaks when the capacitor and source voltages are equal and opposite, which occurs at the time represented by this vertical line and again by this vertical line. So we have a peak here, actually a valley, not a peak here. And again, the reason the current is zero at the point where the capacitor and source voltages are equal and opposite is simply that the voltage across the resistor is the source voltage minus the capacitor voltage. The source pushes in one direction, the capacitor voltage pushes in the opposite direction. This means that the current is zero here, and it'll again be zero here. The current is positive when the source voltage exceeds the capacitor voltage, so that's going to occur. Positive current is going to occur up to this point, so we're going to have some curve for the current. Comes along here like so, and then becomes zero again here after having a negative peak or a valley halfway between these zeros. And we can see from this curve and this curve how the current has its zeros half a phase before the capacitor does. So we say that the current is zero this far before the capacitor is zero. This far is half of this distance, which is the distance between consecutive peaks and valleys of the capacitor. So this distance is half a cycle. So the current lags the capacitor by half a cycle. Said a little better, the current lags the voltage of the capacitor by a quarter of a cycle.